Let's do an example of that. So in lab, you guys threw a test lead into one of our big magnets, ran some current through it, and it jumped around a bit. So I'm going to draw big magnets. So example. So these are the red-blue magnets. So we get a north pole, and we get a south pole. Field lines come out of north poles, go into south poles. That. We ran a wire through the magnet and connected to a battery. Here's my battery. So it gave me a current going that way, and we saw a force. So, let's see. The only part of the wire that feels the force is the part in the magnet. So there's L. Whoops. We let the width of the magnet be script L. And if you measure stuff, our magnets, script L is 7 centimeters. For the magnets that were red blue, now we've got a couple sets of magnets floating around lab. We're going to do the more powerful ones. Those magnets, we measured the field to be 0.2 Tesla. And the current you got through here, because you've killed all my batteries, is probably about 2 amps with our D cells in their current state. I need to introduce a coordinate system, so let's use this one. The one we have been using. X, Y on the board and Z on the page. All right, so now I'm going to write out B and L in vector form. So the vector B is this B naught, its magnitude, and it points in the minus Y direction. The vector L is a vector from one end of the wire to the other, but only the part that feels the field. It's only the part of the magnet. And it points in the minus X hat direction. And it's L long. So the force, the current, L cross B. And so we just substitute stuff and do the cross products. This is an easy cross product. I minus L x hat cross minus B naught y hat. Minus signs cancel. We pull the L and the B naught out, and then X cross Y is Z. So we get I L B naught Z hat. So we get a force out of the board. Let's see. L cross B is out of the board. That's right. All right, and we can plug in some numbers to find out how big the force is. We have 2 amps, 0.07 meters, 0.2 Tesla, Z hat. Is 0.056 newtons Z hat. Okay, so not gigantic, but not zero either. Okay, now we've got a force, which means I can do all the stuff that I did with electric fields, with magnetic fields. I can start putting stuff in the field and asking the direction of the force, or the direction of the rotation of the magnetic dipole, which we'll get to later in the lecture. Okay, so I'm going to take my wire carrying current out of the board, and I'm going to draw the field. On the direction field with the right-hand rule, field rotates like that. And now I'm going to start shooting particles in the field. So let's take this point, and I'm going to shoot a particle with that velocity, and we'll let it be a positive charge, so maybe a proton with that velocity. And so the next thing I have to do then is read the field map to see the direction of the magnetic field at the location of the charge. So the field comes around like this, so when the field hits that point, B points that way. So for that setup, the magnetic force is 0, because the angle between those two vectors is 180 degrees, and sine of 180 degrees is 0, so over here, the force is 0. So now I'm going to pick a situation where the force isn't 0. Same positive charge. Now I'm going to shoot the velocity into the board, like that. The particle is being shot into the board. At this point, the magnetic field goes up like this. The force is QV cross B. So, use the cross product and point our fingers towards V, QV. Q is positive, so QV is in the direction of V. Bend my hands so the fingers rotate towards B and my thumb points in the direction of force. Now, if you're using the other form of the cross product, the finger points towards QV, just like that. I rotate my thumb so the middle finger points towards B and my thumb points towards the force. Now, some of you doing cross products pretty well, some of you are still working on it. So it's a good time, this week is a good time to either use lab time or to have your TA help you with the cross product in office hours so you get good.